we looked at the higher order derivatives. There was a question about the meaning of those f sub x y or f sub y x. Let's take a note here. F sub x y is the same as f sub x, and now taking the derivative with respect to y. It is also the same as delta f over delta x and y, of course. And now we take the derivative with respect to y. So those are the different notations one may use as well. Right. So let's talk about that theorem that I mentioned earlier. When are those mixed derivatives, partial derivatives, equal to each other? And they're equal to each other if we have f that is defined on an open set in R2, and it can be expanded to larger sets as well. And the partial derivatives have to be continuous. Then those mixed partial derivatives are the same. Theorem. That f we defined on an open set in R2, where f sub x y and f sub y x exist and are continuous. On that open set, then we have f sub x y of x and y is equal to f sub y x of x and y. So all we need is continuity of those partial derivatives, and then we can exchange the order of differentiation. So let's do an exercise on that. Okay, so we have f of x and y is equal to square root of x times y. So if I take the derivative with respect to x first, then I would get with respect to x, what would that be? Times what? Y, exactly. Just put the y up here. If I take f sub y of x and y, now if I take the derivative with respect to y first, I get the same, but with an x here, 2 square root of x y. Now if I take the derivative with respect to y, f sub x y of x and y is equal to, I will have to use the quotient rule, right? I will get 2 square root of x y minus y times derivative of 2 square root of x y with respect to y would be what is it, x divided by 2 square root of x and y times the 2 that we already had here, divided by that denominator squared, so we will get 4x y. Let's just cancel out. Here we have x xy divided by the square root of xy, which is equal to square root of xy, so that is equal to square root of xy divided by 4xy. After simplifying. Alright, what about f sub yx of x and y? Well, if you follow through, you will see that that is actually exactly the same. So you would have to do the same thing over again. Let me do that where I have some more space. So we have f sub y of x and y is equal to x divided by 2 square root of xy. So now we have f sub yx of x and y is equal to, if I take the derivative with respect to x now, I'll have 2 square root of xy minus the derivative of that expression now, x times derivative of 2 square root of xy with respect to x would give me the 2 y divided by 2 square root of xy. Those 2's cancel out. Divided by my denominator squared, which is 4xy. And well, here I have xy divided by square root of xy, which is equal to just square root of xy. So I get again square root of xy divided by 4xy. So that would be the derivative. And you see that it's the same as f sub yx of x and y. And there are more exercises of that same type that you can check. Right, let's move on to differentiability. What does it mean now that the function is differentiable? Definition. We say that the function z equal to f of x and y is differentiable at point AB, provided that f sub x of a and b and f sub y of a and b, that they exist. And the change delta z. Delta z was the difference in the z values, right, between pointers coordinates xy and pointers coordinates ab, is equal to f sub x of a and b times delta x plus f sub y of a and b times delta y plus epsilon 1 delta x plus epsilon 2 delta y. Given that that change is equal to, do you remember that formula? You've seen that in one-variable formulas. We use that to make approximations. Also, when we talk about the mean value theorem, you should have seen that one too. Anyway, this is like a little error term, and those have to go to 0. They're going to be really small, so if you want to approximate that change in your z component, is look at the product of the partial derivatives and the delta x, partial derivative with respect to y and the delta y, and that's going to give you an approximation of the changes in your z's. I hope you've seen that before. Okay, let's continue. Where for fixed A and B, epsilon 1 and epsilon 2 are functions of delta x and delta y only. Okay, so they cannot, those epsilons cannot depend on anything else but delta x and delta y's. And that vector epsilon 1, epsilon 2 has to go to 0, 0. As delta x, delta y goes to 0, 0. As those those variables, delta x and delta y, go to 0, epsilon 1, epsilon 2 depend only on those. That vector of epsilon 1s and epsilon 2s has to go to 0 as well. Easiest is probably to look at it in one dimension. So if you have here a function, you look at an approximation over here, you're approximating that value. That would be, this one is a, f of x is equal to, maybe I should write this bigger, f of x is equal to f of a plus f prime of a times x minus a. That would be the approximation. And the exact value over here is f of x is equal to f of a plus f prime of a plus times x minus a plus epsilon times delta x. So that difference here is delta x. So that would be the exact value. And of course that epsilon here, that epsilon would have to go to 0. So now in 2 dimensions, or where our domain is a 2-dimensional vector space, we have the 2 epsilons which have to go to 0. It goes back to the definition for a limit. If you think about the epsilon delta groups here now, as you get closer and closer with your x towards a, the difference between the function and its approximation has to get smaller and smaller, meaning that epsilon has to go to 0. So it's said to be differentiable now. The function on an open set is differentiable at every point in the open set. Differentiable at each point in that set. So now it's kind of hard to test that, right? If the function satisfies that condition. That is non-trivial. So the conditions now for differentiability are that the partial derivatives exist. Yeah, that's good, but that's not enough. Just existence of partial derivatives is not enough to say that the function is differentiable. What we need also is that the derivatives are continuous. So if the function has continuous partial derivatives, then we say the function differentiable at AB. No, don't copy that. If f of x and y has continuous partial derivatives at point A, B, that means f sub x of x and y and f sub y of x and y are continuous at AB, then f of x and y is differentiable at point AB. Continuous partial derivatives. So how can we check that? Well, we take the partial derivatives and check if they are continuous using the rules for continuity that we discussed earlier. And if it turns out that those derivatives are continuous, then you can say the function is differentiable. Okay, so how about we have number 28, we have 3x squared y to the negative 1. Minus 2x to the negative 1y squared. So I need to find f sub x. If I take the derivative with respect to x, I will get 6x y to the negative 1 plus 2x to the negative 2y squared. And f sub y of x and y is equal to, taking derivative with respect to y, I get negative 3x squared y to the negative 2 minus 4x to the negative 1y. So where would those functions be continuous? Exactly, yeah. So continuous when x is not equal to 0, y is not equal to 0. So that means f of x and y is differentiable on part2 without that point with coordinate 0, 0, without the origin. What does differentiability mean? That it's continuous. If it's differentiable, then it's continuous. And then continuity, of course, is going to apply integrability, right? So for us, for now, we'll just establish that if a function is differentiable, then it's also continuous. Theory. If f of x and y is differentiable at AB, then f of x and y is also continuous at a, b. So, let's see, there was one interesting example. So, there's an example in your book which goes over the existence of partial derivatives, but that function is not differentiable at that point 0, 0, because the partial derivatives are not continuous at that point. So the example they give you is f of x and y, which is 3xy. F of x and y is equal to 3xy divided by, what's that, x squared plus y squared. If x, y is not equal to 0, 0, and it is defined as 0 if x, y is equal to 0, 0. Let's use proper notation here. That's how you would write it. So you can show that f sub x and f sub y exist at 0, 0. But they are not continuous at 0, 0. And that means that f of x and y is not differentiable at 0, 0. So for you, the exercises on the homework are mainly taking partial derivatives. So you get to practice. Again product rule, quotient rule, chain rule, some of those. You just have to remember if you're differentiating with respect to x, treat y as a constant. If you're differentiating with respect to y, you treat x as a constant.
Then we have three variables, x and y.
Yeah, you will have also functions and more than just two variables. There are some examples in the book. Let's do one of them. We have f of u vw is equal to u over v plus w. Therefore, u vw is equal to u over v plus w. Now you can find f sub u of u, v, and w, which would be equal to 1 over v plus w. F sub v of u, v, w, if I take the derivative with respect to v now, I like to think of it as u times v plus w to the negative 1, so I will have u divided by v plus w to the negative 2, no, 2. And f sub w of u, v, and w is So let's just check. If I took here the derivative with respect to W, f sub u w of u v w is equal to derivative with respect to w gives me 1 divided by v plus w squared. If I take here the derivative with respect to u now, that is equal to, if I take it now with respect to u, I will get also 1 over v plus w squared. You can see that those two are equal again. Why? Because those partial derivatives are continuous. Yes?
F of v and w should be negative.
Did I miss something?
Yeah, two partial derivatives.
Yeah. Why? Because I had to bring the negative 1 out. So that would make that one here also a negative, and that one negative. Yep, thank you. You need more examples of that? No? Okay. Then we can move on to the chain rule. Yes?
Before we move on to chain rule, are we going to be able to see a practice test for testing?
Yes.
Okay, I can email you one, but it's going to be tomorrow. If you are not signed up for iMail and you need special email arrangements, you either sign up for iMail or you ask a neighbor to forward that to you, please. Okay? Can you do that, please? That way I don't get 10 different emails with that same file. All right. Just sign up for iMail. That's all the information I have to send out. If I'm one day sick and I want to email you so you don't come in here at 7:30.
You don't get sick.
Yeah, I hope that too, but then it would be easier if I had your email and I could just email everybody. Right, so let's talk about the chain rule. Sometimes we have functions that are compositions of functions. You've seen those before. Like for instance, you have again a surface, and let me see. We have that surface, and so that would be a surface in R3. Where we have our x-axis, our y-axis, and our z-axis. And the surface here, z is equal to f of x and y. So now in that plane, I can pick a path going from point P to point Q. If I project that one onto my plane, I would like to know what is the rate of change as I'm going from point A to point B, or P to Q. So where I have r of t, that curve is equal to some function with respect to t. Of course, it's going to have x of t coordinate and y of t coordinate. So really what is changing over time is going to be the t, and with it, it's going to change that path that I'm taking on that three-dimensional as time passes. I'm going down that mountain on a certain time road. And I would like to know what is the rate of change. What's the delta z as time changes? So for that we will need the derivatives. So so we have z, which is actually z of x and y, which is equal to z of x of t and y of t, because those are changing over time. So what I'm interested in is, first of all, is z a function of one or two variables now t is changing? No, it's just one. It just depends on one variable, that is t. Z is a function of t. So because z is only a function of t, I'm interested in dz over dt. So we have z up here. We have partial derivatives. We have x and y. So we need delta z over delta y. And we will need delta z over delta x. And now each of those, actually I've written it here, depend on t. So I will have to find the delta dx over dt, and I will need to find dy over dt. And so they depend on. So t is an input into x is an input into z, t is an input into y is an input into z. So it follows that dz over dt is equal to delta x over delta z over delta x times dx over dt plus delta z over delta y times delta dy over dt. You will see that the result is the function 1